Hi, today I'm going to talk about junction field effect transistors, or JFETs. Before I do, I need to give a quick review on how solid-state devices work, and particularly how diodes work, because JFETs are very closely related to diodes. If you're jumping into the middle here, you probably want to go to the beginning of solid-state devices to make sure you understand what I'm talking about, because this will just be a quick review. So, we know that solid-state devices are typically made out of silicon or germanium, which forms a crystal structure that is not conductive. We call them semiconductors, but when they're in a crystal form, they're not conductive. But we can diffuse impurities in there that make them conductive. So I'm going to draw a line here because I'm going to have different impurities on the different sides here. And on the right side here, I'm going to infuse impurities such as arsenic or antimony or something that is going to add an extra electron. So silicon and germanium have 4 electrons in the valence shell, and they form a covalent bond, a very strong bond that binds the electrons into the crystal structure very strongly, so they are non-conductive. But if we put just a few atoms of arsenic or antimony or anything else that can give 5 electrons, has 5 electrons in the valence shell, and therefore will have an extra electron for every atom we put in there. Those extra electrons don't fit into the crystal structure, and so they tend to float around. They want to remain near their atoms, but they can move around rather freely, so it becomes conductive. So I'll just draw a few negative signs over here to represent a few arsenic atoms that are diffused into this intrinsic silicon over here. And because it has extra electrons and electrons are negatively charged, we call this N-type material. So there's N-type over here. On the other side, we're going to put some materials that have 1 too few electrons in the valence shell, such as aluminum or gallium. And every place where one of these elements is, we have a place in the crystal structure where there could be an electron, but there isn't. And that missing electron in the crystal structure is very attractive to electrons, and so electrons will tend to hover around there that don't belong to the atoms that are in the structure, and so they are free to move around. I'll draw each one of those as a little circle. We call them holes because they are literally holes in the crystal structure where an electron could be but isn't. And over here we're not going to follow the electrons because that becomes confusing if we do. But when an electron moves from one hole to the other, it appears that the hole moves in the opposite direction. I use an illustration of a golf course where we have a putting green where there's a hole here, and you putt out, your ball goes into the hole. Next day you come, and as they often do, they've moved the hole to keep the green in good condition. They don't want people being in the same place all the time. And you putt in and you think nothing of it. You say, oh, well, they moved the hole. Did they move the hole? No, they took some grass and dirt from over here and moved it over there. Grass and dirt is what moved, but it looks like the hole moved. And when analyzing p-type material that has fewer electrons than expected, it's actually easier to follow the holes than to follow the electrons. So we consider the holes to be charge carriers over here. They carry a positive charge. So we have holes as charge carriers that can move electricity. And over here we have electrons as charge carriers that can move electricity, if you will. So we have the stage set. We have electrons as charge carriers over here and holes as charge carriers over here. And remember, these holes are very attractive to electrons, and these electrons are free to move around. And so near this junction between the p-type and the n-type material, these electrons are going to jump into those holes and fill them up. And so if there's electrons in those holes, are there holes there anymore? Nope. So now we have an area between there and there where we have no charge carriers. So this becomes a non-conducting piece of material. And we call that area the depletion region. I'll just put a DR there for the depletion region between the holes in the p-type material and the electrons in the n-type material where there is no charge carriers, and therefore that's a non-conductive area. Now let's see what happens if we put a negative charge on the inside and a positive charge on the p side. And what that means is that I have a battery in there oriented like that. And what's going to happen is when we put a negative charge on the inside, that is going to repel these electrons and it's going to drive them toward the junction. And we put a positive charge on the P side, that's going to drive the holes away and drive them toward the junction. And what happens? Well, when those holes get too close to the electrons over here, what's going to happen? The electrons are going to jump into the holes and they're gone again. But in the meantime, we're injecting new holes from the positive charge and injecting new electrons from the negative charge. And so as those electrons jump into the holes and we have currents flowing, holes flowing this way and electrons flowing that way, we get a continuous current flow. But that has nothing to do really with junction field effect transistors, so let's do the opposite thing. Let's put our depletion region back in there, get rid of our extra holes and our charges, and we'll just get rid of the battery. We know that's going to be there when I talk about reversing the charge. Now let's put a negative charge on the P side and a positive charge on the inside. Well, this positive charge is going to attract electrons toward it, so these electrons will move away from the junction and toward the positive charge. Likewise, this negative charge is going to attract holes, so the holes will move away from the junction and move closer to the negative charge. So what happened to our depletion region? It got bigger. So if we put a bigger positive charge here and a bigger negative charge, in other words, more voltage differential, that's simply going to draw the electrons and the holes further from the junction. So we have this depletion region that can grow or shrink depending on how strong of a reverse bias charge we put on the diode. So we have a depletion region and a non-conductive area that can grow depending on how much reverse charge we put upon this diode. Well, that's interesting. We have a conductor here and a conductor here and a non-conductor there. Doesn't that make a capacitor? Yeah, it does. Then if I change this charge and change the distance between those conductive areas, don't I make a variable capacitor? Yes, I do. Diodes that are optimized to take advantage of that are called varactor diodes, but that's not what we're interested in. But another thing we can think about is, well, I have a conductive area here that, depending on how much charge I put across it, that conductive area might be this big, or I put a stronger reverse bias charge on it, and that conducting area gets smaller. Could I make a variable resistor by changing how much conducting area I have here based on the voltage, and therefore have a voltage-controlled variable resistor? Yes, I can, and that is called a junction field effect transistor. It's a little more complicated than that, but we'll get into that in a moment. So let's redraw. This is getting a little cluttered there. So here is our intrinsic material with our junction, P-type material, N-type material, and I'm going to, instead of putting an electrode here, I'm going to put two electrodes, one there and one there, and we'll put an electrode on the P side right there. So now if I put, well, let's put our holes in here, just to remind us how this is working, and our electrons over here, to remind us how it works, and we're going to have our depletion region, let's not forget about that. So if I put a negative charge here, and let's say put a positive charge here, just one place at this time, so that is still going to reverse bias this diode and going to make the depletion region bigger, so these electrons will be drawn over here, making the conductive region smaller, and being smaller it's going to have more resistance. So I have basically between here and there a voltage-controlled variable resistor. So let's just take a little more look at how this is going to act. And first of all, how are we going to actually bias this? Well, obviously I'm going to have a battery over here biasing that, and I'm going to need another battery over here to bias this. Well, of course I'll use other circuitry to create the voltages necessary, but notice I have a negative side of the battery here. There's negative, there's positive, and then there's positive, and there's negative. And so I have it biased that way. And, well, I'm going to call this ground because I can. So I have negative voltages and positive voltages. But remember, negative voltage is not the opposite of positive voltage. It is just a voltage that is lower than something that we have decided to call 0 volts. So this ground is just a 0 volt reference. Helps us visualize what we have going on here. Okay, a negative voltage, that's going to be, let me just draw a battery here just to remind us of what a negative voltage is. There's a couple of batteries, and I'm going to not draw a circuit in here, but we have positive to negative, positive to negative. And so I have my highest voltage here and my lowest voltage here. Let's say these are 5 volts each. If I put a voltmeter across here, I'm going to see 10 volts. If I put it there, I'll see 5, there 5. And if I put my negative lead right here, if I put my positive lead there, I'll see plus 5 volts. What will I see if I put my positive lead there? Negative 5 volts. It's just simply a lower voltage, and I've decided to put my black lead here because 0 volts is wherever you put your black lead. So basically what I've done is I've put my black lead here, so that's 0 volts. Anything higher is positive, anything lower is negative, and there's my lower voltage. So that's all that is. And I said that just to explain one thing about my biasing I have here. Well, this is positive, this is a lower voltage, that's an even lower voltage. So this is still positive, just not as positive as this. So there's my most positive voltage. There's a lower positive voltage. It's 0, but remember, it's just a lower voltage. And there's my lowest voltage. So this is positive compared to that. This is positive compared to that. So I still have that reverse bias situation with positive to my inside, N material and P material. And so now I can control the width of my depletion region by how, I'll just make this a variable battery, how strong is that negative charge there. So this becomes the control of how big my depletion region is and how big my conducting region is. Let's just throw a capacitor in here and throw some kind of an input. So we have a particular voltage here. Let's make that minus 5 volts just to have a number there. And so if this voltage goes up, what's going to happen? That's going to become, well, maybe negative 3 volts. Becomes less negative as I push that voltage up more positive. As that voltage comes down, it's going to go up higher. So it might go up to plus 7 volts. So as this voltage goes up and down, it's going to take that voltage up and down. And so as this goes more positive, this becomes a more positive, less negative voltage. The depletion region gets smaller, I get more conduction. And as this voltage goes down, I get less positive or more negative, and the depletion region gets smaller and less conductive. So with this arrangement, where the N-type material is where my conducting channel is, which is called an N-channel FET, as this goes more positive, it conducts more. As this goes less positive, it conducts less. And I'll just draw the symbol for that right here. That's the symbol for an N-channel JFET. And you can remember that because the arrow is pointing in. And so basically I have N material and P material and making my N-channel JFET. Another thing to remember, of course, is this is reverse biased. So how much conductivity do I have between this point and this point, or that point? Very, very little. So I have almost no current flowing into or out of the controlling lead of this JFET here. So that's the basic idea of how a junction field effect transistor works. I guess I should give these names. In a bipolar junction transistor, we would call this the collector, the emitter, and the base, but we don't call them that in a field effect transistor. This is the drain, this is the source, and this is the gate. So conventional current goes into the drain, conventional current comes out of the source, and the gate is the controlling lead of the field effect transistor. And if I reverse these, if I have N material here and P material here, I have a P-channel transistor. And of course, then I have the arrow pointing outward on the P-channel. So remember, on the N-channel JFET, the arrow points in. and it does not on the P channel. So there is the gist of how they work. Now, once again, I'm not going to go into actual circuits with this, but I will talk a little more about some characteristics of it. So let's get rid of our drawing here. And let's talk about, let's draw a N-channel J-FET here. And we have our drain, our source, and our gate. And we want current to conduct from the drain to the source. And how much current conducts is going to be dependent on the voltage at the gate. Now let's draw a little graph here. And what I'm going to do is put a battery across here. It's getting a little cluttered on the bar, getting a little cluttered on the board here, but we'll make this work. This is going to be, this axis here is going to be our voltage from the drain to the source, or the VDS. So this is going to be a variable battery here. And we're going to see what happens to the current through the drain to the source as I change that voltage. Now I'm going to get this out of the way because it's kind of in the way of my graph a little bit here, because that's the voltage from the drain to the source, and this is going to be the current from the drain to the source. We'll just call it ID just to be consistent with standard nomenclature here. So that's our drain current, how much current goes into the drain compared to how much voltage is between the drain and the source. And this acts like what? A resistor. So let's say that I have, let's put 1, 2, 3, 4, 5 volts here just for a voltage. And let's say our current is 1, 2, 3, 4. Let's call it milliamps because we can. And so we see that at a particular gate voltage, let's say I have 1 millivolt here. That's going to be minus 1 millivolt. So as this voltage becomes more negative, I'll get less conduction. So let's say here I get a situation where at 1 volt I get 1 milliamp. And at 2 volts I get 2 milliamps. 3 volts I get 3 milliamps. Let's see if we can draw this in a straight line here, because that's what we will get. So that's going to basically give us a straight line as we increase this voltage across here. Let's put our battery here again just because we can. Remind us that there's a variable battery there. As we increase that voltage, we increase our current, and like a resistor, it's going to go in a straight line. We double the voltage, we double the current. Except we don't, but we'll talk about that in a moment. And so let's make this even more negative. Let's make it minus 2 millivolts. And what we're going to see is that this is going to get less conductive. So let's say at that point, at 1 volt, we get a half a milliamp. At 2 volts, we get a whole milliamp. At 4 volts, we get that, and we get a straight line. So it looks like a resistor. And if we reduce this voltage here, we'll get more current with more voltage. So as we increase our voltage across the back of the transistor, we get more current, and acting like a resistor, these will be straight lines. Except this doesn't act that way. What's going to actually happen is with our different gate voltages, this is going to flatten out. That'll flatten out. That will flatten out. Let's do one more, and that will flatten out. So each one of these curves is a different gate voltage. So let's make this one, let's make this minus 1 millivolt, minus 2 millivolts, minus 3 millivolts, and minus 4 millivolts. Now I'm completely making up these numbers, but it gives us a realistic view of how this will work. So what we're saying now is if I put minus 1 millivolt on the gate, now as I increase the voltage from the drain to the source, it doesn't act like a resistor because it starts going in a straight line, but then it flattens out. As I decrease, I followed the wrong line there, it's going to act like a resistor, but it's going to flatten out. As I increase this voltage, It's going to conduct a little less, but it's still going to flatten out, but it's going to flatten out in different places. So it doesn't quite act like a resistor. In fact, what happens is I get a saturation situation. Remember, saturation is when I increase my input, I no longer get a change in the output. So what's happening here is that this begins to saturate. As I increase my voltage, I no longer get a change in the output current. So we call this area the saturation region. And what we get is a predictable current based on the gate voltage. So once I have this biased correctly, I don't have any biasing set up here, so we're kind of making up the numbers, but once we get some real numbers out here, we'll get something very similar to this, where a particular gate voltage will give me a particular drain to source current regardless of the drain to source voltage. So I get a saturation. Well, is that useful? Yeah, it looks very useful to me. I get a particular current based on the gate voltage. But down in this area, it's still acting more like a resistor. It's not going into saturation, and so basically I get a particular resistance based on the gate voltage. So we call this the resistive region. So I can use a field effect transistor, whether it's a J-FET or a MOSFET. I talked about those in a different video. We have a region where we can treat it like a variable resistor and get different resistances based on the gate voltage and do with that whatever we need to. And if we need something where our resistance is important, we can operate in this region, meaning we don't have a very high voltage across the back of the transistor from the drain to the source. So we keep the voltage here low, it acts like a variable resistor. But if we raise that voltage, then we find it acting more like a transistor, where instead of our gate voltage controlling the resistance, our gate voltage controls the current. And so therefore the resistance is changing to make sure the current stays the same regardless of the voltage here. When I do the small signal amplifier video, I will use my little green man model to show how he would think this over and operate it and control the resistance here to get this effect with higher voltages and this effect with lower voltages. So that is basically what we have with a junction field effect transistor. So just a quick review. A J-FET works like a diode. I'm going to draw it differently here because you'll usually see it drawn more like this. There are different ways to illustrate a J-FET. And so I have a P region here and an N region here. There's my drain, my source, and my gate. And so now I have a depletion region in this area here. Now, you'll usually see this depletion region drawn a little differently. I'm going to make it bigger there than there. Why? Because this is more positive. Let's make this really positive. That's more positive than that. So compared to the gate, which is negative, both the source and the drain are positive, but the drain is more positive than the source. So we get a bigger depletion region here as there. Does that make a difference? Not really. It's just a different way of illustrating it. And as I increase this voltage, that depletion region is going to get bigger. Oh, and there's one other thing. What happens when that gets so big that it completely blocks the conduction? We call that the pinch off voltage, when this voltage gets to a point where we actually turn off the conduction altogether and basically have an open switch. It's pinched off. Sometimes people will draw a J-FET like this. I don't think this is very realistic, but you will see it where there we go. So now we have two P regions, one big N region, and two depletion regions, and they might pinch off the channel. I don't know what good it is to draw it like this, because even if you look at how a J-FET is actually manufactured, let's take a look at an idea of how that's done. We have a piece of silicon. We diffuse in some P-type material, if it starts out as N-type material. We diffuse that in, and then we have some connections here and here. So that's basically a realistic construction of how it's going to be made. And so now we have our depletion region here and our conducting channel going like that. So this is more like how it's actually manufactured, not too unlike my illustration here. But anyway, as this becomes more negative, our depletion region gets bigger. Therefore, we have a smaller conducting region. And so the more negative this is, the less it conducts. The less negative it is, the more it conducts. And of course, if we put a signal here, as that goes more positive, this becomes less negative, of course, and vice versa. So more positive means it conducts more, less positive means it conducts less for the N channel. Of course, if I want to make a P channel, everything's just reversed. Big negative, small negative, and now this is going to be positive. And it's just the voltages are reversed, and just like the difference between a NPN transistor and a PNP transistor, just all the voltages get reversed. I'll get more into that when I talk about small signal amplifiers down the road. So that's the basic idea of the junction FET. It's basically a diode with an extra terminal on it, because controlling the voltage between the gate and the source, we control the size of the depletion region, therefore controlling the size of the conducting region. And we have what amounts to a voltage-controlled variable resistor, except if the voltage is high enough between the drain and the source, that saturates, and so we end up with a current that's proportional to the gate voltage, as opposed to low voltages here where we have a resistance that's proportional to the gate voltage. So that is junction field effect transistors. So I hope you found this useful and informative. If you did, please give me a thumbs up down below. It really helps the channel. And don't forget to subscribe and hit that bell when you do so you get notified when I put up new videos. And if you want to take my free course in electronics technology, go to vocademy.net and take the course. Sign up, read the material, watch the lectures, take the exams, and follow your progress. And when you're finished, you'll be a good candidate to become a certified electronics technician. Or you can get a jump start in your studies as an electrical engineer. To help me put these videos online and help me keep Vocademy free, you can go to patreon.com/Vocademy and pledge your support. The smallest pledges help me do this. And a big thank you to my patrons at Patreon. I could not do this without your support, and thanks to everyone for watching.